Hello everyone. Good afternoon. So today we will be starting the functional materials part 2 of this advanced material chemistry course. So since a lot of classes you have attended, so and you were just attending the functional material part 1 course. So in this part 2 course we will be covering the photovoltaics, solar energy, energy conversion, fundamentals of semiconductor physics and other things. Then there will be thermoelectric materials, fundamentals of thermoelectricity, seabed.
Excuse me, ma'am.
Yes.
Ma'am, was there any class yesterday? Because I tried to join.
No, not yesterday. Day before yesterday there was a class.
Actually, ma'am, there was no class on Monday also, right?
Yes, on Monday there was no class. That class was postponed and it was there yesterday. So Dr. Dimple Datta took that class yesterday at the same time. So I hope if you have missed it, then you can always attend it on the YouTube. You will find it there at the Anu Vidya portal. And if still you get any problem, then you can let me know in my next class. So we will see what we can do about that. Okay.
And ma'am, I have submitted the assignment also.
Okay, thank you. So that we will see. So this is the other module. This is the fourth module we are starting. You already have module from Dr. Vinita Gupta, Dr. Barik, Dr. Dimple Datta, and now I am starting the fourth module, which is the functional material part 2. So as I was saying that I will be covering the photovoltaic materials, their fundamentals of semiconductor physics and photovoltaic cells. Then there will be other part on the thermoelectric materials, so fundamental of thermoelectricity, Seebeck coefficient, Peltier, Thomson effect, and how thermoelectric effect is generated and how it is used. And then we will be talking about the device-worthy materials, which will be like semiconductors, elemental semiconductors, compound semiconductors, and how these semiconductors for a device application are grown into single crystals and thin films. So basically this I will be covering in 6 lectures. But today I am not going to take it in the chronological way as shown here in the course structure. I will be starting with the fundamentals of semiconductor physics because a basic understanding of semiconductor physics and the device and PN junction is required for all these parts. So I will be starting with that. And then in my next lecture, I will be starting on the single crystal growth technique, like the float zones, Ekrolsky, the theory of single crystal growth. My third lecture will be on the thin film deposition techniques because these are the basic how to make a device and this will be required. And then we will be going to the photovoltaics and the thermoelectric materials. So this will be how I will be covering the 6 lectures. So today I will be starting with the semiconductors, so fundamentals of semiconductor material. So first thing is like why this whatever I will be covering today, you will find that it is very basic, basics of semiconductor physics and all, which you must have learned in your plus 2, 11th, 12th and in your BSc, MSc also. But I will be covering it because just to brush up and so that some if there is any lag is there, and since you are going to start your PhD program and coursework you will be all doing, so just basics, it's always good to brushing up. So starting with material, how generally whenever anyone asks you how you will be like asking whether it is a semiconductor or not. So because the word semiconductor, it is comprising of two things, that is the semi part and the conductor part. The semi part and the conductor part, it means that the electrical conductivity of this material is in between the metals and the insulators. Okay, so that is why it is a semiconductor. So at room temperature, the metals have the highest conductivities and it is of the order of 10 to the power 7 per ohm meter. And which will is followed by the semiconductors, which is around in the range of like resistive conductivity is 10 to the power minus 3 per ohm meter, and the resistivity is less than 10 to the power 5 ohm centimeter. And finally, there are the insulators which have got very high resistivity and very low conductivity. So conductivity is like 10 to the power minus 11 per ohm meter, and the resistivity is very high, 10 to the power 5 ohm centimeter. So in the left hand side, you can see this panel where I have just chalked out a few materials, like in case of metals, we have got silver, copper, gold, aluminum, tungsten. So we see that the resistivity is very low, 10 to the power minus 8, minus 7 of this order, and conductivity very high. And then we have got alloys also, nichrome, constantan, like these are used for various application of that same order, minus 7, minus 6 resistivity. But when we go to semiconductor, so if you see the resistivity, other than carbon, the germanium and silicon, which are more known as the known semiconductors, we see that the resistivity is like 0.4 or 640, which is very less for silicon. And then we come to the insulators. So where the resistivity is very high, like for a wood, it is in the range of 10 to the power 8 to 10 to the power 11, whereas rubber is 10 to the power 13, glass is 10 to the power 14 around, quartz, which is fused silica, is around 10 to the power 7. So this is just how the resistivity is changing, but our material of interest is the semiconductors, so which we will be studying today. Now, why is this kind of conductivity? Why we are observing this kind of conductivity change in conductivity? So semiconductors is, what is a semiconductor? So the second thing is that we have now differentiated the materials as per the conductivity, but there is also anyone, if I ask you like what is the other thing, how you can differentiate material, you will be saying that it is depending on the band gap. So first is the conductor, in which the valency band and the conduction band, so they are overlapping the form, and it is electrons are filled on the Fermi level. Then we come to the semiconductors, in which the energy gap is of the order of around 1 eV or slightly higher than that, and we have the valency band which is filled at room temperature and or at 0 Kelvin, and the conduction band is empty. Whereas in case of when we come to an insulator, the band gap increases, so which is around 9 eV or 6-7 eV, and at room temperature it has got filled valency bands, and the conduction band remains empty even at higher temperature, because the energy gap is very high. So it is very difficult for any electron to jump from this state to this state, so the conductivity remains very less. So when an allowed band is completely filled with electrons, the electron in the band cannot conduct any current. So when an allowed band is the valency band. Metals have a high conductivity because the large number of electrons that can participate in current transport, because the conduction band, they are in the conduction band. Most of the electrons are there in the conduction band. And semiconductors have zero conductivity at 0 Kelvin, but as the temperature increases, their conductivity also increases. So these are the things which, why this is happening, what is the basic phenomena, and this difference is there. So taking the case of semiconductors, we will try to understand this. So if you see whatever we have studied earlier in the earlier two slides, the same I am again saying that we have the conductor, we have and how the conductor is behaving, and we have the semiconductor. So in case of conductor, resistivity versus temperature, we see that as the temperature increases, the resistivity of the conductor increases, and at very low temperature. So this is, we are having this from 0 to 300K, we are having this temperature range. But if we see just this part, so this is like 0 to 20K. So at very low temperature, we have got some resistivity in case of some conductor, and then it keeps on increasing. It is a parabolic behavior initially at low temperature, and then it becomes a linear. So as you know, for conductor, they don't have really zero, it is not like zero resistivity or at zero temperature, because this resistivity is because of some of the impurities which is present for a given conductor. But when the temperature rises, so the resistivity also rises in the conductor, because there will be more collision of the electrons with the ions because of the thermionic vibration in the lattice, and because of that the resistivity increases. But if we see for a semiconductor, as we are increasing the temperature, so temperature is increasing, the resistivity is decreasing. So resistivity is decreasing. Why it is so? Because we have seen in the earlier slide, we have got a conduction band and we have got a valency band in a semiconductor, and this at T at sorry at t equal to 0, this is empty. This is empty. And all the electrons are in the valency band. But as T increases, so electrons start jumping to the conduction band and we get conductivity. So, and these electrons which are there in the conduction band, they can conduct the current. So that's why the resistivity falls. So resistivity versus temperature for a typical conductor, the linear rise in resistivity while increasing temperature, but at very low temperature, it is different. So resistivity versus temperature for a typical conductor at very low temperature is the curve flattens and approach a non-zero value at t raised to t tending to 0, and this is because of the impurities present. Now, when we talk about the resistivity versus temperature of a typical semiconductor, it increases dramatically as the temperature increases. But then why it is so? But before I go into why this observed behavior is there for the semiconductors, so the journey of semiconductors, like today, if you see, everything is dominated by semiconductors. From your mobile to the computer on which you are watching my lecture today, the core, the heart of everything is the semiconductor technology. But it started not very long back. It started on 24th December 1947 here, when Bardeen Shockley invented the first bipolar transistor in the Bell Labs. So here you can see this is the photograph of their actual bipolar transistor which they made. So this was a germanium crystal on which they took the top contact, and there was a and this is the copper base. From this where they took the base contact, and it was a quartz base was kept. So metal base is there. Here the germanium. Here you can see this is the germanium crystal, which is this one, and then they have got a gold foil on this, you can see it here, and the base contact is this, the copper plate, and through this the two contacts were taken and they started. So this is the journey started. So using this double point contact, they made it onto a germanium crystal and took the voltage to 90 volts, and they saw. So this just to show that this is their original writing. If you can, this I am showing how they have done. So we have attained the following AC values at 1000 cycles. So energy gap and all. So this is the starting of the transistor and the semiconductor journey. And this was further Jack Kilby made the first IC circuit. So this is the start of the modern electronic era. So here you can see this is the first IC. This is the first IC which was made, and this is how your smartphone IC board looks like. So from this to this we have come, and as of like in 2016 it is said that largest transistor count in a commercially available single chip processor is over 7.2 billions. So that is how important this is, and the IC chips from this to this genre is there. So we have to understand that what are the characteristics of the semiconductor was there, because of which it became so important. So now to understand the characteristic of a semiconductor, I would like that we go back to the band theory of solids, just understand very basics of it, why the band theory come, what is the basics of band theory, and on the basis of that we understand the semiconductor. So we know that this decreasing resistivity with increasing temperature and all those things we can understand if we look into the band theory. So essential feature of the band theory is that the allowed energy state of for electrons are nearly continuous over certain range called the energy band. Like earlier also I was showing that we have got a conduction band and we have a valency band. But actually, is it like that for a semiconductor, or how it is forming? Because when we are talking about a silicon or germanium, or say starting with a hydrogen, so we have got this energy levels like 1s, 2s, and so on. So how from 1s, 2s it is we are going into this band? So if we see in this figure, we see that we have got like separation of atom is there on the x-axis, and let us say that we have got any atom is there which has got electron in 1s level and 2s level, and so at when the separation is very large, so they are existing and their electrons are there in the 1s and 2s separately, but when they are coming closer, so this splitting is there. So 1s and 2s energy levels start splitting for an hydrogen atom, like for two atoms we have got. So here you can see like we have got this 1s and 2s level for 11 hydrogen atoms are there. So we have got splitting for 11, they are splitting into 11 bands. So why it is happening? So if you see here, same case is for the silicon. So why it is happening that when two atoms are coming close, so there is this splitting. So basically this splitting is because of the Pauli's exclusion principle. So what our Pauli's exclusion principle says, it says that for any given substance or a material or a system, no two electrons can have the same quantum state. So everyone should have a different energy level. Now if we go back to our earlier slide, so if we take case here, so we have got two electrons here, and let us assume that we have got two electrons, one electron each in, so we have got one, we are considering the case of a hydrogen atom, say. So we have got like 1s, we have got one electron, and there are two hydrogens or two atoms are there. So when they are very far apart, they can have their independent energy level. But when they come close to each other, like we have got, if I show it here, we have got 1s electron is there and 1s electron in another hydrogen atom. So this can come, they can have the same energy because now they are like at a different distance and they have got different energy, same energy level. E1 is same as E2. So if you say this is 1 and 2. But now as they start coming closer to each other, they will start overlapping. And there will be this electron will start affecting the energy levels of this, and similarly this will also start affecting the energy level of the other electron. So because of this they have to go into different energy levels, so therefore there is a splitting of all possible energy levels. So when we come to the case of a silicon, we say that an isolated silicon atom has got 14 electrons. Okay, so we have got n is equal to 2, 8 electrons, n is equal to 1, 2 electrons, and then outermost shell n is equal to 3, we have got 4 electrons. Okay, now as we know, and this is the nucleus. So these two shell n is equal to 1 and n is equal to 2 are deeply, they are the core shells. So when another silicon atom is coming, so and coming close to here, so its shell, only the outer electrons will start affecting each other, whereas this will be shielded. So these atoms will not get affected from because of this silicon atom. So out of the 14 electrons, only 10 occupy deep lying energy levels whose orbital radius is much smaller than the interatomic separation in the crystal. Okay, that is clear for them. The 4 remaining valence electrons are relatively weakly bound and can be involved in chemical reaction. The 3s subshell, this is the 3s. N is equal to 3 and L is equal to 0 has 2 allowed quantum state per atom. This subshell will contain 2 valence electrons at T is equal to 0. So we have got 2 here. The 3p subshell, that is N is equal to 3 and L is equal to 1, has got 6 allowed quantum state. So this one will have 6 allowed quantum states, and this will contain the remaining 2 valence electrons of an individual silicon atom. So this is for an individual silicon atom. Now we have got, so we are talking about this kind of interatomic distance for there is only one silicon atom there. Now what happens when they start coming closer to each other? So when n isolated silicon atoms are brought together, as the interatomic distance decreases, the 3s and 3p subshell, this 3p and 3s, we have got that, of all the n silicon atoms will start to interact and overlap. The 3s and 3p levels merge into a band containing 8 n states. Because we said that because of the Pauli's exclusion principle, here we can see that they, like if we have got n is equal to 1, so if this, when the interatomic distance is less, so all they will be having a slightly different energy levels. So the energy level of the new material which is formed because of the merging of all the atoms will be having, from this n is equal to 1, they will be having this much energy level. Similarly for n is equal to 2, because we are having more number of atoms, so this is getting split into all this. So each atom will be having a separate from the other one, and similarly here. So when we have got this 2 electrons in the 3s state and 2 electrons in the 3p state, so we have this 4 n states now. When we are getting n silicon atoms are merging together. So at the equilibrium interatomic distance, so this is around this. Due to the condition of minimum total energy, the bands will again split with 4n state in the lower band and 4n in the upper band. So they are coming together. So they will be merging here, but any time any system will try to have a minimum energy state. That is the law of nature. So they will again break and form 4n state and at the high energy level and 4n state at the low energy level. So this is leading to the formation of the energy band. So earlier we were talking about the valency band, about the conduction band, but now we see here clearly why it is happening. So again, at the equilibrium interatomic distance, due to the condition of minimum total energy, the band will again split with 4n states in the lower band and 4n in the upper band. Okay. So total there are 8n, because 2n are here, 6n are here. Though only number of electrons are 4, but the number of energy levels which are allowed is 8. So 4 goes to the higher energy state and 4 goes to the lower energy state. At absolute zero, all the electrons will occupy the lowest energy state and all the states in the lower band will be full. So all the 4 electrons will be here and this will be empty. Okay. And at 0 Kelvin. The lower band is called the valency band and upper band is called the conduction band. The bottom of the conduction band is called EC. So this becomes our EC. And this becomes our EV. So this is EV and this is our EC. And the difference between this is the energy gap. The difference between the two energy is the band gap energy Eg of the given semiconductor. And Eg is the energy required for an electron to jump from the valency band to the conduction band. Means if we are giving all the electrons are there in the valency band. So if we give this much value to any electron which is sitting in the valency band, it will go to the conduction band. So this is formation of bands in silicon and how we have got the valency band, how we get the conduction band, and how when we are giving any energy to the electron, it jumps from the valency band to the conduction band, and as the name suggests, conduction band, so it will start conducting. So this is just the basic of how the conductivity in the silicon or in any given semiconductor is different from a conductor. You have understood, you have seen that how we are differentiating different materials based on the conductivities and the energy band. And now we will go to the next section. But before I go to the next, if there is any question from anyone, just let me know. And I will just take 1 minute break here and again come back. You be ready with your questions and then we will go forward. Okay. So, any question from anyone? Okay, so I think it was very basic. So now we will go forward. Depending on this, just we have got the band structure. We have got the conduction band, the valency band for a, and we have got this energy band gap. Now at 0 Kelvin, what happens? We have got the valency band is full. So electrons are there in the valency band and there is the conduction band is empty. And then we have got, as the temperature increases, so we have got electron hole pair creation by the thermal excitation. So the electron will jump. So we have seen earlier, we have got the Eg. So valency electrons will jump from Ev to Ec and leave behind the hole. So using the, and both the electrons and the holes can be used for the conduction of electricity. So at the temperature rises above 1K conduction, 0K conduction band electron in number of conduction band electrons increase, and but at zero temperature, zero absolute zero temperature, the silicon behaves like a insulator due to empty conduction band. As explained, the number of conduction electrons in an intrinsic semiconductor depends exponentially on Eg and the absolute temperature. When a conduction electron is thermally generated, a hole is also generated. A hole is associated with the positive charge and free to move around in the silicon lattice. Now, the earlier slides, we were taking that valency band and the conduction band as a pictorially. But when we are going into the quantum mechanics, so if we plot the energy momentum case space, so the band structure is something like this. We have got the parabolas. So this is the energy and this is the K momentum. So here we have, so depending on this this is called the band structure of the semiconductor. So EK relationship. So in semiconductor physics, so we are interested in the properties of the EK relationship near the top of the valency band. So this is the top of the valency band and the bottom of the conduction band. And depending on this, there are two types of semiconductors. So one is called the direct band gap semiconductor, another is called the indirect band gap semiconductor. So I will be coming to this two definitions later on also. But as you can see in this pictorial representation, that when the conduction band minima and the valency band maxima comes at the same K value. Sorry. So both is coming at K is equal to 0. So it is called the direct band gap. But if the conduction band minima is at a different value of K, so it is called an indirect band gap because K is at a different. So if there is any electron in the valency band and it has to go to the conduction band, so it will go to some state here and then it will go. Or if it is jumping back from the conduction band to the valency band, so first it has to come to K is equal to 0 and then come back. So this is the indirect band gap. Other one more thing here you can see is the curvature of this. So here we have shown you two curvature. So if the curvature is more, so it is called the effective mass of the holes, or if it is in the conduction band, effective mass of the electrons. So this is called M star. So if the curvature is more, like we have got more curvature, so we will call it is having higher effective mass. For higher curvature. And when the curvature is less, so it is got lighter hole or lighter electron effective mass. So how it will be translated in the properties of the semiconductor? So we'll coming to that. The top of the valency band occurs at k is equal to 0 in most semiconductor. There can be two different kind of EK curves near the valency band edge, labeled the heavy hole and the light hole. And the bottom of the conduction band in some semiconductor occurs at k is equal to 0, and they are called the direct band gap semiconductor. This is gallium arsenide, indium phosphide. So I will be coming to them. But if the bottom of the conduction band does not occur at k is equal to 0, the semiconductor is called indirect. So what we are using now, silicon and germanium, the most abundant semiconductor and mostly used semiconductor, they both are indirect semiconductor, indirect gap semiconductor. The alignment of the valency and conduction band edges has important consequences. The direct band gap semiconductor has a strong interaction with light. This is a result of the law of momentum conservation. So I will be coming to that later. Now coming to the materials, which are the semiconductors. So this carbon group, these are the most important semiconductor materials. Our silicon is there, germanium is there. Then we also have got tin. So why they are semiconductors? Because they have got 4 electrons in their outermost shell. But there are other also important materials which can used in the semiconductor industries. So silicon, germanium we have seen, but we can also, there are other materials like boron is there. So third group element, fifth group element are also important, and we have got the fourth group. So important semiconductor is like silicon, germanium we have seen, and this is their band gap. Another is carbon, but carbon has got many allotropes. You know that we can have a diamond, we can have graphite, graphene is there, and then we have got normal amorphous carbon is also there. But diamond, the crystalline form of carbon, is a semiconductor. But now we come to the compound semiconductors like the gallium arsenide. So what we are seeing that this is the gallium and this is the arsenic. So these two are combining to form a semiconductor because gallium has got 3 electrons and this has got 5 electrons. Okay, so when they both combine, so we have got 8 electrons in the outermost shell. And this is very much like 2 silicon atom. So gallium plus arsenic. So that's similarly we have got gallium plus nitrogen, gallium nitride. We have got indium phosphide, boron nitride, silicon carbide. So these are all the compound semiconductors and these are the elemental semiconductors. So semiconductor composed of a single species of atom like the carbon, silicon and germanium are found in the fourth column of the periodic table. They are the elemental semiconductor. Whereas the compound semiconductors are composed of 2 or more elements can also be there. Like we can have gallium, indium, phosphor. Gallium, indium, so or gallium, indium, arsenide. So we can have a combination also of them. So in this way, we can, for example, gallium arsenide, aluminium, antimony, and indium antimony are all 3-4 group semiconductor. Similarly, we can also have 2 and 6 group semiconductors. So the combination of the elements are so that when both the elements 2 are combined together, they have got average of total 8 electrons in their outermost shell. And this is how the compound semiconductors are formed. Now, when we will be going forward, we will see that the compound semiconductors, because in case of the compound semiconductors, we have got the liberty to see or check the elements which we want to take. Like we can have gallium with arsenic, we can have gallium with nitrogen or with phosphorus. So in that way, we can change there or tune there or tailor the properties of the semiconductor. So what kind of properties are they will be, like the band gap and the energy gap is there, one thing, like what kind of parabola, like ek parabola is there, so it can become more faster or something. So we can tailor the properties as per our application. So that's why nowadays the compound semiconductors are becoming very important. At the starting, when this semiconductor journey started, as you saw, I have shown you that Bell Lab first, that the transistor, bipolar transistor, that was based on the germanium. So germanium was used in many early devices. But later on, silicon replaced the germanium, mainly because it is higher band gap energy, low cost, because silicon is present in nature as silicon oxide, which is nothing but the sand, and it can be extracted easily, whereas germanium is very less, and it can be very easily oxidized to form silicon dioxide insulating layer, and for making the ICs and all, it is very easy to do. So that's why silicon started replacing the germanium. Now we will take the case of a silicon and see how the conduction is there. So we have already seen that silicon has got four electrons in the outer shell, which are the valence electrons, and therefore it can form covalent bonds with four of its nearest neighbor. So we have one silicon. So say silicon, this electron belongs to this electron belongs to this, and this electron belongs to this, and this electron belongs to this. So it has got, and then it can form four covalent bonds with its neighbor. So like in the middle one, we can see that it can form covalent bond with four of its nearest neighbor. When these are the four covalent bonds. So all the electrons which are there are bounded to the silicon lattice. So when the temperature goes up, so these electrons can become free and start moving about the silicon lattice. And so we have got the silicon. So as we increase the temperature, so this electron becomes free. So it was there earlier in the valency band. Now it has gone to conduction band, and it can move through in the lattice of the silicon. So as the temperature increases, so because of the temperature, this electron has become free and this is moving in the conduction band. So as more and more temperature increases, the thermal energy shakes an electron free and the conductivity increases. So this is an intrinsic silicon. All at t is equal to 0, all the electrons were bonded, but at t is equal to greater, when the temperature is increasing at a temperature greater than 0 Kelvin, the electrons are becoming free and it is showing conductivity. But then we can make other arrangements to make the electrons available in the conduction band, and that is through doping. So before we go into the doping, we see that in semiconductors, creation of an electron and hole pair is necessary for generation of electricity. And hole is nothing but a missing electron. So it can be taken as an excessive positive charge. When an electron and hole comes in contact, they annihilate each other and they become neutral. These electrons and hole are the majority carriers, charge carriers, because they are the charge particle which carry the current in the semiconductor. Therefore, semiconductors can conduct electricity at temperature greater than 0, but not much current. Huh? So we may think that okay, just increasing the temperature only we will get lot of conductivity. but it is not so. If we see that at room temperature, we have got only one free electron per 3 trillion atoms of silicon. So that is not much of conductivity. So what is the different way we do to increase the conductivity? We dope it. So we have got two type doping. So first let us check with the N type doping. So we have seen the silicon lattice this there. Now we have removed one silicon atom and we have put one phosphorus. Phosphorus has got 5 electrons in its outer shell. So 4 are being bonded with the silicon. 4 silicons are there surrounding it. So 4 are there, but 1 electron is remained to migrate. So adding impurities to the silicon crystal lattice leads to the increase in the number of carriers. And for this we have to add very less number. Add a small number of atoms to increase the number of electrons or holes. So in this case we have putting phosphorus, which is a column 5 element, and this replaces the silicon in the crystal lattice, and there is now an extra electron in the structure, though the structure is still charge neutral, but very little energy is required to free the electron for conduction, since it is not participating in any bond. So we have got this kind of N type material. So positively charged is there. These are the silicon atoms are there. Negatively charged electrons are there, and they are the majority carrier. And we also have some holes are also there, because the electrons which have jumped to the conduction band because of temperature, they will be leaving some holes. So we have got, but they are minority carrier because their number is less. So the phosphorus atom has donated an extra electron, and this can move freely, and it also leaves behind a positively charged nucleus which cannot move, and overall the crystal is electrically neutral, and the concentration of donor atoms, that is the number of phosphorus atoms, is around 10 to the power 5 to 10 to the power 20 per centimeter cube, and this electron is free to move in the crystal with an mobility of around 1350 per centimeter square per volt. So this is huge mobility, and just by adding a very few number of atoms like 10 to the power 5 to 10 to the power 20 per cc atoms of phosphorus, we are able to change the electrical property of this material. But this is like fifth group. Now we can also use third group element like boron, which has got 3 electrons in its outer shell. So what is happening? It has got only 3. So 3 bonds are there. 1, 2. This is from this silicon. So this is not there. So this boron is 1 bond, this boron, and this is 3 bonds are because of boron, and here it is empty. There is nothing here. So there is now an incomplete bond pair creating a vacancy for an electron. So little energy is required to move a nearby electron into the vacancy, and by this, when this electron goes into the vacancy, the hole will propagate. So we have got this hole is propagating, right? So if we can see here, first the hole was here, now it has gone here, then it went here, and then it went here. So basically, in this way the conductivity will be there in the material. So as the hole propagates, the charge move across the silicon. So this is called a p-type silicon material. So we have got hole which is propagating inside the material. So p-type material we have got, now you can see these holes are the majority carrier, and we have still got some electrons which are the minority carrier. And we have got, now in case earlier we had got which are the positively charged ions were there, now we have got negatively charged ions, which cannot move in the, because borons are there, boron is there left behind, silicon is left behind. So because of that we have got the positively charged negatively charged, sorry, not negatively charged ion in the system. So when we add atom with only 3 valency band electron, the acceptor electron accepts electron and provides an extra hole to freely travel around. It leaves behind a negatively charged nucleus, and overall the crystal is still electrically neutral, and the concentration is the, so but here you see the mobility is less. In earlier case, you have seen that the mobility of the electron in the silicon lattice was around 1300 degree per centimeter square per volt, but whereas it is just 500, because movement of hole requires breaking of a bond. So it has got low mobility. So obviously if we are conducting through holes, then the mobility is less. So we have to see what kind of application we are looking into. Now we have got the N-type material which has got electrons as a charge carrier, and we have a P-type material, P-type semiconductor which has holes, positive holes. Now what is happening when we are bringing this N-type and P-type together? So this is just a small animation you see. So initially this is their Fermi level. So we have got the Fermi level here and here. So when two types of semiconductor comes into contact, electrons flow from the N-type to the P-type. So electrons will be starting flowing here, and the holes will flow from the P-type to the N-type. So this is now the new energy band diagram. It happens. So we can see that the N-type region is now connected to the, and when we will go back and we will see again. So we have got this two band. And now the N-type region. So here how it is that electrons are there in the N-type region and holes are there. So they are now connected. So the energy barrier for the holes to move into the P is positive. So they can go here. Similarly, electrons can come here. So energy barrier for the electrons to move to the left. This is the energy barrier, and this is for the holes to move to the right. Now, and this is the depletion region. So this part is called the depletion region, and this is our EF, Fermi energy level. Now, if the N-type region is now connected to the positive terminal of a battery, so further deformation of the band occur and the electric energy barrier is increased. So we will see how it is happening. Okay. So now the N-type region is connected to the positive terminal of a battery. So how things will change? So you see this a depletion layer. So the now earlier it was like this, now it has increased. So this is called the reverse bias situation. So energy barrier for both electrons and holes have now increased. So energy barrier for the electrons to move to the left and energy barriers for the holes to move to the right. It is now, it has increased, and this has also increased. So the electrons will not be able to flow easily to the from the conduction band of the p type to the conduction band of the n type, and similarly holes will not able to migrate. So because of this, the semiconductor is called to be reverse biased, and the depletion layer is increasing. Now if we bias it in the opposite way, so instead now we have got n-type material is connected to the negative terminal and p-type to the positive terminal. So this is the forward bias, and results the energy band is now reduced. So energy barrier for holes to move to the right side, and energy barrier for the electron to move to the left side. So now the energy barrier is very less, and also the depletion layer has gone down. So this is the forward bias. So using this band diagram, we can understand how when we have got a P and N junction, so how the energy band is changing under the forward and the reverse bias, and why it conducts. So you are very much aware that if we have got this is a PN junction, so it is a diode. So nothing but PN junction is nothing but a diode. And how does the IV characters look like? So if this is V, this is I. So in the positive, so some energy band is there, and then it starts conducting. Whereas in the reverse bias, it is very less, and then there will be breakdown. And exactly like this, some energy is always required. That is the energy band, and this. So this is the diode characteristic. Now operation of a PN diode is like, so we have got holes are there, electrons are there, n-type material. So the current conduction is, when we are giving this, p-type is to a negative and n-type is to a positive voltage. So electrons will be moving in this direction, holes will be moving in this direction, and there will be, and when it is forward bias, we have got recombination of holes and electrons at the junction will be there, and we will be having a net current in this case, whereas the net current in this case is in this direction or very less. So operation of a PN junction diode, this is first is the no bias. There is no bias. So the small thermal electron current, because only of the temperature IT, so is offset by the electron recombination current. So net positive current is 0. With a DC voltage applied as shown, the diode is now reverse bias. This one was there. Now IR is slightly less than IT. Thus there is a small net flow of electron from P to N and positive current from N to P. In the final case, the diode is forward biased, and because current can readily flow from P to N, IR can be much greater than IT, and this is how a diode conducts. So I think till now you have understood this are because very normal topic. So I will take 1 minute break here, and then we will start with the different semiconductors. So we will be joining in 1 minute, and if you have got any questions or anything, any doubt is there, we can take up then, and then we will start the next part. So till now, I feel that you don't have any questions. So let me ask you one question. We saw that PN, no, forward bias and reverse bias. So can you tell me why reverse bias is important, or any device where the reverse bias PN diode is used? So please let me know. Someone can put it on the chat or tell me. Huh? Is it important that reverse biasing is important? You have any application where that reverse bias diode is used? No one knows, or what is the application of diode? And all diodes used in just forward bias, or reverse bias diodes are also used? So it looks like there is no one to answer. So maybe this I'll keep as a question for next lecture, and you all have to give me answer like one application where forward bias diode is used and where a reverse bias diode is used. Okay, so I want everyone's reply. All of you who are attending the class has to give this question, answer, reply this answer. Now coming to the different materials and materials of interest, so which is there. So we saw that the fourth group element are there. The silicon is there, germanium is there. So silicon is the backbone of the semiconductor industry. It is an elemental semiconductor. You can see this, it has crystalline solid with its melting temperature is around 1400 degrees centigrade, and materials, generally SiO2, which is the sand. So this makes silicon the second most abundant element in the Earth's crust, around 28% by mass after oxygen. So that was the main reason of silicon, one of the main reason, not the only main reason, one of the main reason why silicon as a semiconductor gained more importance than what was the other? What was the other semiconductor? That is the germanium. Though the story started with germanium, and germanium we see it is a lustrous, hard, brittle, grayish, white metalloid kind of thing. It was. It does not. It is not present in the earth crust as it is. It is present as a form of an ore. So this mineral argyrodite is there, from which you have to take out the germanium. First time it was taken out. Now its average concentration is around 1.6 ppm. So you can see the contrast, silicon, which is the second abundant material, and compared to that, germanium is just 0.16 ppm in the earth's crust, and you have to extract it from the ores. So generally germanium is present in fly ash or zinc ores, so all those things. And both of these are the elemental semiconductor. But these are very high important materials of economic importance is there. And this is just to give you an overview. So if we see nowadays, you all must be hearing that no, rare earths are dwindling, or India is not able to get the rare earths. So these four zones are there, which is by government of India. They have seen keep what is the relative economic importance of the material on the x-axis, and the supply risk means getting them. Are we getting them easily or not? So zone 1 are the highest economic importance and high supply risk material is there, and in this we get both silicon and germanium. Okay, so both this material are of high economic importance and high supply risk. So germanium content is around 10 milligram per kg in zinc ore and core fly. So this there is a lot of work has been started to get this material from the ore and have and the industries are there working on the making this material or growing the crystals for this. So if we can see that silicon crystals, so when we this all the PN diodes or a transistor or whatever you have seen earlier or studied earlier, so we required the silicon single crystal or the germanium single crystal for this. So either germanium or the silicon. So here you can see the germanium single crystal. This is the silicon crystal, and this silicon crystal is cut and polished into wafers on which we are making the ICs, right? And if we see that the semiconductor crystal growth, this accounts for more than 60% of all single crystal applications. So in the next class, we will be talking about the single crystal growth and all. So we will see that most of the single crystal growth techniques are has advanced because of their application in the semiconductor industry. So around 60% of material crystals are dedicated to semiconductor. Then we have got around 12% as scintillator, 10% as optical materials, like calcium fluoride is there, all those things. Another 10% for acousto-optic. Then we have got around 5% for lasers like ND, arc, ruby, and then jewelry. So vast bulk of the solid state devices are still silicon based, not germanium based, silicon based. So here if we can like compare the properties, the band gap of germanium is very less, 0.6, whereas silicon is 1.12. So less band gap, what does it mean? That you will have more number of charge carriers at a given temperature, because it is very easy for an electron in a germanium to jump from the valency band to the conduction band at any given temperature. You have to give very less temperature for to have conductivity. So that is in a way good also, but in many cases you will get, because of that you will get noise. So unwanted carriers are there. Whereas in case of a silicon, because of high band gap, it has got better stability, less noise. Now energy required to make one electron hole pair. So for silicon is around 3.76 and for germanium is 2.96. Now the thing which is important thing to understand is that, like if we take this case, though the energy gap is just 1.12, so we have learned that this is EG, right? Band gap energy gap. But if we give just 1.12 energy to silicon, we will not get an electron hole pair. We will only, this is average value, but when that value is around 3.76, energy is required to make one electron hole pair in silicon. So some energy is lost because of the because of phonon energy and all those things. Now electron mobility and hole mobility. So electron mobility in germanium is much higher than the mobility in silicon, and similarly hole mobility in germanium is also very high. So this mobility, we saw the EH curve, right? Remember? And I told that if you have got two semiconductor with two types of curvature, so for the flat curvature, the effective mass is higher. Say this is 1 and this is 2. So this is higher than M2. So in case of a higher effective mass, it will be having less mobility. So the band gap, the EK curvature for the silicon is more. So that's why its mobility for both electron and hole is less. Now we come to other material, which are the compound semiconductor. So they are made of two more elements, unlike the semiconductor made of a single material such as silicon. So in the compound semiconductor, we combine elements from group 3 and group 4, or group 2 and group 6. And elements from group 4 also we can add. So we have got like gallium arsenide, indium phosphide, indium gallium aluminum phosphide, and silicon germanium. So compound semiconductor are used in device having higher mobility. So high mobility, why I will be explaining that. But what leads to high mobility? What application we can go for if it has got higher mobility is like high frequency devices or high switching or high efficiency than a single element semiconductor such as silicon, and have a wide band gap. And the band gap for this compound semiconductors you can tailor, and we can have a wide band gap. And having a wide band gap, how it is important is like we can go for high temperature operation or high voltage resistance due to the strong bond force between the atoms. And these compound semiconductors can have good optical properties and used in LEDs. Okay. So when we say that advantages is higher electron mobility, so electron moves faster in compound semiconductor compared to silicon. So because of that, we have got faster switching speed. This is crucial for high frequency electronics like RF amplifier, 5G in 5G and radar system. Low power consumption, because already the electrons are moving very fast, so we don't need to put lot of voltages. So faster electron movement can lead to more efficient operation in certain devices and lower power consumption. Because they are having wider band gap, so this allows some compound semiconductor to handle high voltages and operate at high temperature because without breaking down. Then because of this, because they can handle higher voltages, so we can use them in high power electronics. Like silicon carbide is excellent in power converted and switches used in electric vehicle and renewable energy system. Then light emission they can be used. So silicon and germanium, because they are indirect band gap, so they cannot give out photons when the electron jumps from the conduction band to the valency band. But gallium nitride being uh, first, it is wider band gap and it has got direct band gap, so it can be efficiently used for LEDs. And blue LED is based on gallium nitride. And certain compounds like the indium phosphide emit light efficiently at specific wavelength, making them valuable for laser and detectors. So we will just see what are the different applications of each of the compound semiconductors. So gallium arsenide, it was one of the first widely used compound semiconductor, and it has got high electron mobility, which allows electron to move through the material very easily, ideal for application that require high speed and in such as in microwave circuit. The compound is also used in some transistor and high efficiency solar cell. Now coming to the gallium nitride, it is known for its wide band gap. Its wider allows it to handle higher voltage and operate at high temperature because without breaking down. And that's why ideal for use in high power and high frequency electronics like RF amplifier, 5G radar. I already told that. Now coming to another important material is the silicon carbide. So slowly in high power devices, you can see that silicon carbide is replacing silicon. So it is for power electronics due to its excellent thermal conductivity and high breakdown voltage. So here we are getting a compound semiconductor where both are coming from the fourth group elements. They are not like 3, 5 or 2, 6. They are both fourth group. So the combination of properties allows silicon carbide to operate efficiently at high voltages and current for power switches. Then we have got indium phosphide. So it is optical property is very good and high electron mobility. Desirable for high speed optical communication, and because of the optical properties, lasers and detectors used in fiber optic network. Now we have got aluminium, gallium, indium phosphide. So we have got a lot of materials here, a lot of elements are there. So this is basically engineering of the material. It can be band gap engineering, or we are just compounding the material. So combinational material sciences, they are coming into play to tune the materials band gap. Also the amount of each, stoichiometry, 1:1:1 of all this, or like if we are increasing P slightly more than all other elements, so it becomes a P-type semiconductor. If we are increasing the concentration of aluminum in it, so it becomes a N-type sorry, I'm talking opposite. If we increase the phosphor in it, it becomes an N-type semiconductor. If we increase the aluminum in it, it becomes a P-type semiconductor. So just adjusting each element's proportion in the final alloy, it can be made into a different type of semiconductor and can be made to emit light in different colors. So particularly red and orange. So it is a valuable material for LEDs. So from here we can see that though elemental semiconductors are important, but lot of things are coming up using the compound semiconductor. So we have seen the crystal of silicon, and which is grown, we will be talking later, by the, so it is also grown by Zekrolsky technique, and the vertical gradient freeze technique is also used for gallium arsenide. So both these techniques we will be learning in the next class, which is on the single crystal growth. Now gallium arsenide has a direct band gap. So what is a direct band gap? Means the minima of the valency band and the conduction band both is at K is equal to 0. So this property enables gallium arsenide to convert electricity into light and vice versa. Means when the, since it is like this, so whenever a electron in the conduction band jumps to the valency band, so it gives out a photon. This gives out a photon, H mu. Or similarly, we can give a photon and it can go there directly. So where there will be no loss. So this makes it ideal for optoelectronic devices that rely on the light electricity conversion. And as compared to silicon, it has, which is the workhorse of electronics, gallium arsenide boasts high electron mobility and fast electron. So this is an important material and upcoming. Now, this direct and indirect band gap, we have been talking about this again and again, and we have seen that for silicon, germanium, and gallium arsenide. So, but what exactly, just very little I will tell about. The particle momentum for a free electron is 0 when the kinetic energy is 0. So, at K is equal to 0, the kinetic energy is also 0. So an electron at the conduction band minima can have crystal momentum different from 0. So here it is different from 0. So in silicon, which is an indirect band gap, silicon is an indirect band gap, silicon or germanium. So it makes a transition from the valency band to the conduction band. It requires not only an energy change, so from valency band to energy band. So it has to go here, not here like this, because it is indirect band. So it requires not only an energy change, this is the energy change, but also a change in the momentum. So basically it has to go here, or it has to go here and go here. So both energy and momentum change is required in case of a indirect band gap semiconductor, which is not required for a direct semiconductor. So here I have shown the band diagram, energy band structure for silicon and gallium arsenide. So this is the valency band maxima for both at this is K value. So this is K is equal to 0. Gallium arsenide being a direct band gap, so this is its conduction band minima. Silicon conduction band minima is here. So though the energy band gap is 1.1 and 1.4 here, so there is a difference. And we can also see that the curvature for silicon, this curvature for silicon is very high, whereas for a gallium arsenide it is very less curvature. So effective mass is like 0.067 for the gallium arsenide as compared to silicon. It is less, effective mass is less. So that means the mobility will be higher. Now, if we can compare, so the main disadvantage of this compound semiconductor is difficult for the fabrication. If you are making the crystal, it is very difficult to maintain the stoichiometry and all those things. So similarly, when we compare for silicon and gallium arsenide, so it is difficult to process, whereas silicon is relatively easy technology and well established technology, and it has got indirect band gap, and gallium arsenide has direct band gap, so superior electronic band structure. Band gap we have seen it is around 1.4 and this is 1.1. Because of this indirect, you have poor optical properties, so it will not like give out a photon when an electron from the conduction band will jump to the valency band, whereas for gallium arsenide it has got excellent optical properties. But still silicon is prevailing in the industry is mainly is high quality of native oxide, that is SiO2. SiO2 is very stable. It forms on the surface of the silicon, stays like that, so that it prevents any deterioration of the device which is underneath. So, and it does not, gallium arsenide does not have this kind of. So now we have got like silicon, germanium and gallium arsenide. So electron effective mass is very less for gallium arsenide. If you can see 0.067 of electron, this is times electron. Whereas for silicon we have 0.9 at a different temperature, and this IT and DOS is at the different values we have seen that. So I will not go very detail into it, but because of this effective mass very less, so mobility is very high for gallium arsenide, and that's why it is so important. Similarly, for hole mobility also, gallium arsenide has got very high mobility. Band gap we have got for silicon, for germanium and gallium arsenide. So germanium finds application where we want a small band gap material, or germanium is generally cooled at low temperature to suppress the thermionic current. At 77 Kelvin we have got this, and for silicon it is 1.17 and this is 0.7. So generally, like in case of radiation detectors and all, germanium is used at 77 Kelvin, where we want the dark current to be very less. Means when there is no application of electric field, the current is very less. In very less means less than nanoampere. Now energy hole pair production is like 2.96 in case of germanium. So because of this property, it can be used for energy detection, like in radiation detection, whereas it is quite high for a silicon. So with that, I come to the end of today's class, and as I have asked that one application each of you will mail me on the positive bias and the negative, forward bias and the reverse bias for a diode. And we will have 5 minutes of question answer session before we stop this today's lecture. So please let me know what are the confusions, or you want to see something or discuss. No questions from anyone? Okay, then we will log off today, and tomorrow, day after tomorrow, we will start with the single crystal growth theory and growth of. We will be looking into all the growth technologies, but more emphasis will be there for the Zekrolski, which is used for growth of silicon and gallium arsenide, as we have seen there. So most of the technologically important device grade materials are made using the Zekrolski or the melt growth technique. But as a whole, we will try to see how crystal growth happens, what is the theory behind the crystal growth, and the techniques. Okay, then thank you. Have a good day.